Hello, 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 and welcome everyone to the Ben's Chem Videos Friday night live stream. This is episode 7, Chemical Kinetics, Volume 4. That's right, we've done 3 volumes of Chemical Kinetics so far, and you may be asking yourself, where can I find those 3 volumes? Good question, I'll give you the answer right now. There's a playlist that I have, it's called Chemical Kinetics Live Streams. The link for that playlist is going to be in the description of this video once it gets recorded and uploaded. So right now I don't have that link available on the live stream, but when it gets recorded, I will have that link available. So we're going to pick up right where we left off with our discussion on chemical kinetics. But before we get into that, I just want to apologize for the abysmal failure that was the beginning of last week's live stream. I didn't even realize, but for 15 or 20 minutes or so, my audio wasn't working. In fact, I need to confirm that my audio is working now. Yes, it looks like it is working. Okay. So what can I say? I'm a noob. I'd like to think I'm slowly getting better at this as I go along. But last week was a very busy week. I didn't have much time to prepare, and I was frantically getting things together, trying to get the stream ready to give you guys something. I think it turned out pretty good, other than that little snafu where I was completely mute for about 15 minutes. But anyway, so if it's all right with you guys, I'd like to go ahead and pick up right where we left off with kinetics. So here we go. So this is Chemical Kinetics Volume 4. Now, just like I did with the last 2 streams, I like to begin each live stream with a review of the previous live stream. So if we just look at a review of last week's live stream, which was Chemical Kinetics Volume 3, the main thing that we talked about last week was the relationship between the rate of a chemical reaction and temperature, right? We were asking ourselves, does the temperature influence the rate of a reaction? Does the rate of a chemical reaction depend upon temperature? And the answer is yes, it does. It is highly sensitive. Rates of chemical reactions are highly sensitive to temperature. So if you recall the rate law equation, now this is something that we went over from the very beginning in volume 1, but it's something that pops up over and over and over again, and so it's worthwhile to revisit it. The rate law equation is that the rate of a chemical reaction is equal to K, that's the rate constant, times the concentration of the reactant or reactants raised to a power, and of course that power is called the order of reaction. Now, the temperature dependence of the rate of reaction is contained within K. It's contained within the rate constant, not the concentration. It's the rate constant. That's the component of the rate law equation that contains the temperature dependence of a reaction rate. And that temperature dependence is governed by what we call the Arrhenius equation, which looks like this. K is equal to A times e to the minus e sub A over RT, where K, of course, that's the rate constant. A is a term called the frequency factor. And then there's the exponential factor, which is this entire thing here, e to the minus e sub A over RT. That's the exponential factor, which includes the activation energy, which I've put in bold because activation energy is very, very important. That's the E sub A term. And then R is the gas constant, and T is simply the temperature reported in kelvins. So we talked about that equation, we talked about how it works, and we even went through an example at the very end where we applied that equation. Looks like I got a message in the chat from Jassim Mal. It says, hi, hello, thank you for joining me. I really, really appreciate your being here, and more importantly, I really appreciate your participation by typing in the chat, so thank you. So just to, again, briefly go over some of the content from last week. I promise it's all relevant, it's all very important. This is sort of an illustration of the importance of activation energy and how activation energy works. So this is a graph of the energy on the y-axis and reaction progress on the x-axis. So for a chemical reaction such as this one, we see here that the energy of the products is less than the energy of the reactants, which means that the reaction is overall exothermic. It's energetically downhill, so to speak. But nonetheless, the energy has to climb up to this point right here in order to get the reaction to work. And this difference between the original energy of the reactants and the maximum in energy that the reactants must climb up to before they can become products, that barrier, it's often called the activation barrier, in addition to the activation energy, that's called the activation energy, right? So that is the E sub A term. Very, very important. So how does that work within this equation? Well, e to the minus e sub a over RT, that is a negative exponent. So basically what that means is that a larger value of the activation energy, e sub a, is going to result in a smaller exponential factor. If your exponential factor is smaller, then your rate constant will be smaller. And if your rate constant is smaller, that means your reaction is going to be slower. Your reaction rate will be lower, right? So again, basically all that means is that a larger activation energy results in a slower chemical reaction, a smaller rate of reaction. Got another message in the chat from Shiva Shiv, says, hi, hello, welcome. I think I recognize your name. I'm not sure if you've been in here before. I'm pretty sure I recognize your name. If you haven't been in here before in my live streams, welcome. If you are returning, welcome back. Again, I really appreciate your being in here. By the way, if anybody wants to call into the show, there's a link in the description of this live stream where you can call in using Discord. If you click that link and follow it and it doesn't work, please let me know. I'm still trying to figure the call-in portion of it out, but I highly encourage not only participation via chat, but also participation via call. So anyway, so that's activation energy. And then sort of the last thing that we talked about in last week's live stream was thermal energy distributions. So this is a plot of fraction of molecules against energy. So basically what this graph represents is a collection of molecules at two different temperatures, which we'll call T1 and T2, where T2 is hotter or higher temperature than T1. And so notice that as the temperature increases, overall on average the energy of the particles or the molecules is higher, as you would expect, because temperature, of course, is a measure of average kinetic energy. But not only does the average get bigger, but also the curve sort of starts to widen, right? I think the term that they use in statistics is variance, right? The variance or the standard deviation gets larger. And so because of that effect, if we consider this dotted line here to be the activation energy or activation barrier, well, any molecule that has enough energy to overcome that barrier can become products, right? If the reactants can overcome the activation energy barrier, they become products. And so you can see here at a higher temperature, there's a much larger fraction of the molecules that is available to become products because that fraction of molecules has enough energy to overcome that barrier. So, okay, so that's a basic review of last week's live stream. So the topic of this week's live stream is going to be something called reaction mechanisms. Looks like I got another message in the chat. It says, what's poppin', guys? A lot's poppin'. How are you doing? Hope you're doing well. Thank you for being here. Really appreciate it. So the topic is reaction mechanisms. So the main idea behind reaction mechanisms is that most chemical reactions do not occur in a single step, but rather through several steps. So if we consider this chemical reaction right here, where we have 2NO2 plus Cl2 yields 2ClNO2, right? If we consider this chemical reaction, what is this reaction actually telling us? Well, it tells us what we start out with, that's the reactants. It tells us what we end up with, that's the products. In other words, we know the starting line, we know the finish line, but we don't know everything in between. We don't know the journey. We know the destination, but we don't know the process by which the reactants become products. And that's what reaction mechanisms tell us. Got another message in the chat from Divyang. It says, hey Ben, it says I was about to start chemical kinetics for my exam. Oh, well, I hope this video or this live stream will provide value in your pursuit of crushing your chemical kinetics exam. And that goes for anybody in here. If you are finding this stream valuable, I would surely appreciate if you slap a like on it. Even send a super chat if you're feeling generous. But all right, let's move on. So the reaction mechanism is more thorough than the balanced chemical equation. It is the series of steps by which an overall reaction occurs. So again, if we take a look at this reaction here that we saw in the previous slide, well, what is the mechanism for this reaction? What is the process by which the reactants become products? Now, the thing about mechanisms is that mechanisms can never be proven to be 100% true. They can be validated, but they can't be proven. And the reason why is because you can't interview the molecules to say, hey, what were you before you became what you are? How did you get from reactant to product, right? All you can do is make a case and build evidence as to what a mechanism is, but you can't prove it to be 100% true. You can only validate it. So keeping that in mind, that's gonna come in handy later on, but keeping that in mind, let's look at the proposed mechanism for this chemical reaction. So there are two steps here. These steps, by the way, are called elementary steps. Most oftentimes you'll just hear them called steps for short, but the technical term for them is elementary steps. So this is the overall, the two-step process by which the reactants in that chemical equation that we saw a moment ago become products. We have NO2 plus Cl2 yields ClNO2 plus Cl. That's step 1. And then step 2 is NO2 plus Cl yields ClNO2, right? Now, one of the requirements for a mechanism to be valid is that the sum of the individual steps of the mechanism must sum to be the overall chemical equation, right? So in other words, when we add steps 1 and 2 together, the sum of those chemical equations must be identical to the overall balanced chemical equation for this reaction. Now, there's a name for substances like this Cl here, right? So notice that the Cl, right, the individual Cl, I'm not talking about the Cl2, but the individual chlorine atom, not the diatomic chlorine molecule, is consumed in the first step of the it's produced in the first step of the reaction, and then it is consumed in the second step of the reaction. And so you don't see any Cl without a 2. You don't see any individual chlorine atoms in the overall balanced chemical equation. But nevertheless, this individual chlorine atom plays a very important role in the chemical reaction. And these types of substances that are produced in one step and are consumed in another, they are called reaction intermediates. So again, there's nothing in the overall balanced chemical equation for this reaction that will tell you anything about the reaction intermediates. If you want to learn about the reaction intermediates, you have to consider the reaction mechanism. So Divyang says, will definitely help. Thanks a lot. Liked. Oh, appreciate it, man. Hey, thanks for your support. And that goes for all of you who are viewing this right now. I really appreciate your being here. And I would appreciate also a message in the chat. That would be cool, just so I can kind of know you guys better. I think that'd be great. So, okay. So we understand now what a reaction intermediate is. It is a molecule or atom that gets produced in one elementary step and then consumed in another, and it does not appear in the overall balanced chemical equation. So if we move on, well, what does all of this have to do with chemical kinetics? Well, chemical kinetics is actually a tool that can be used to understand reaction mechanisms. It's a tool like, let's say you have a chemical reaction that you're studying, and I want to know what's the mechanism for this chemical reaction. What is the process by which the reactants become products? How many steps are there in the mechanism, and what exactly is going on in those individual steps, and what types of atoms and molecules are involved, right? If you want to know that information, chemical kinetics can be a very valuable tool for that. And the reason why is because of a concept called molecularity. Right? So we understand rate laws, right? Rate laws they describe the relationship between the rate of a chemical reaction and the concentration of the reactants. And so if you wanted to look at rate laws for elementary steps, we're going to have to invoke a term called molecularity. Molecularity is simply the number of reactant particles that are involved in an elementary step. So the rate law, right? The rate law of an overall chemical reaction cannot be determined simply by looking at the balanced chemical equation. However, the rate law of an elementary step of a mechanism can be determined from the equation associated with that step. And so, again, molecularity, that's the number of reactant particles involved. You have unimolecular processes. These are the simplest. It's basically just one particle, one molecule decomposing into products. Then we have another type of molecularity. It's called bimolecular, where you have two particles, and there's two possibilities here with a bimolecular process or a bimolecular elementary step. Either you have two particles of the same type, which we're calling A, colliding together to become products, or we have two different particles, which we'll call A and B, coming together to form the products. Now there's a third type of molecularity, it's called termolecular, and that's when you have three particles coming together and colliding. But termolecular processes are actually very, very rare. And the reason why they're rare is because the probability of three individual particles colliding together at the exact same time is very, very low. Nonetheless, it does occasionally happen. And there's three possibilities with termolecular molecularities, where we have three identical particles colliding together, A plus A plus A. We have two of one type of particle and one of another type of particle colliding together, A plus B. And this one down here is when three unique particles, which we'll call A, B, and C, collide to become products. So when we're looking at these elementary steps, right, what we're really looking at is collisions of particles, atoms slamming into atoms, molecules slamming into molecules to produce something different. So if we just look at a summary of the rate laws for the different types of elementary steps based on their molecularity, well, you can sort of see the pattern here if you take a look at this table, right? For the unimolecular process, one particle decomposing into products, the rate is simply equal to the rate constant times the concentration of the reactant. If it's a bimolecular process, where you have two of the same particle colliding together, then the rate will be equal to the rate constant times the concentration of that particular reactant squared. If you have two different particles colliding together in a bimolecular fashion, then the rate is going to be equal to K times the concentration of one of those particles, and also times the concentration of the other type of particle, right? So I'm not going to go through each individual one of these rows. I think you can understand the pattern is that the rate law of an elementary step is going to be K times the concentration of that particle raised to the power of how many particles in that step there are. If there's one particle, it'll just be the concentration of that reactant with no squared or cubed or anything like that. And if it's two particles, it'll be of the same type, it'll be the concentration of that reactant squared. If it's two different particles, then it'll be the concentration of each of those reactants, as we just saw in the third row of this table. Got a message from Victoria. It says, is the reaction intermediate the most unstable part of the reaction? So it would be the highest peak of the energy graph. Sorry if that doesn't make any sense. You know what? That's actually a very, very good question. That's actually a very, very good question. To answer your question, reaction intermediates are generally quite unstable, and they react very, very quickly. This is why elucidating reaction mechanisms is very difficult, because the intermediate is formed and then it gets consumed, like right away, right? But to answer your question, actually, no. The intermediate is not the most unstable part of the reaction. And if everybody else will just bear with me for a second, if we go back to the step with the activation energy curve, excuse me. You know what? Actually, I think one of my future slides in this presentation is going to answer that question. So just hold that thought. It's a great question. Thank you so much for your question. I really, really appreciate it, and I hope I give you a good enough answer, and I hope that you'll stay with me long enough, and I'll try to be brief about it. No promises, but I'll try not to be so long-winded as I usually am. Okay, so moving on. So again, we're talking about reaction mechanisms, right? And we want to know, what is it about reaction mechanisms what is the relationship between a reaction mechanism and its elementary steps to the overall rate law of a chemical reaction? And one thing that will really help us to understand this is to understand the concept of a rate limiting step. Now, It's also called a rate determining step. These are interchangeable terms. They are synonyms. You may know it by this name, rate determining step. Personally, I like to use rate limiting step because it's fewer syllables, it's easier to say, and I'm a pretty lazy guy, so I call it the rate limiting step. But of course, it is up to you, whatever you want to call it, whether rate limiting or rate determining. Anyway, the rate limiting step is the slowest step in the mechanism of a chemical reaction. So generally speaking, chemical reactions that have mechanisms that occur by more than one step, usually one of those steps is going to be significantly slower than all of the other steps of that mechanism. And it's going to limit how fast the reaction can be, right? That's why we call it a rate limiting step. It's like a bottleneck, right? And it's also called the rate determining step because it determines what the chemical reaction rate is. Now, it's at this point that in order to sort of demonstrate the concept of a rate limiting step, I'm going to show you guys a short video from a chemistry teacher by the name of Mark Rosengarten. He's a pretty funny guy. I'm not sure if you've seen his content before, but he's very good. I love what he does. I've actually done some chemistry demonstrations in my classroom based on his videos. So I'm going to show you a video that demonstrates the concept of a rate limiting step. Okay, here we go.
Welcome back to another chemistry tutorial. Today, we're going to be doing rate of reaction. What I've got set up here is an example of a mechanism, the steps a reaction goes through on its way from going to start to finish. This would be the first step, the second step, and the third step of this three-step reaction. What is the reaction? We're going to pour this 2,000 milliliters of green water through these steps and into this, and we're going to figure out how long it takes to do that. We're going to calculate its rate. Now, since I'm going to pour in 2,000 milliliters, we'll figure out how many seconds it takes to go through, and then we'll calculate the rate in how many milliliters go through per second. Okay, are we ready? Keep an eye on the stopwatch right here. And go. Now, as I pour it in, I want to make sure that none of the funnels overfill, because that would be skipping a step. We don't want that to happen. Yay! Whoops! Woo! Almost overfilled that one. Almost there. Oh, almost overfilled it again. And get ready to stop. And not yet. Stop. Okay, how many seconds is that?
36.
36 seconds. So it took 36 seconds for this 2,000 milliliters to pass through these three steps. Now, which of these steps actually held the reaction back? In other words, is the rate determining step. Which funnel, if I could find a way to get rid of, would make the reaction go so much faster? What do you guys think?
The middle one.
You guys agree the middle one? Okay, so let's do that. Let's add a chemical called a catalyst. What catalysts do is they remove steps from the mechanism without getting used up, and watch what happens when we remove this step from the mechanism. We're going to trade off now and pour this 2,000 milliliters in one more time. Okay, we all reset? Okay, here we go. In 5, 4, 3, 2, 1, go! Now, same deal as before, I want to make sure that none of the funnels overfill. Okay, we're almost done, not quite. All right, finger on the button. Now.
20 seconds.
20 seconds. Where's my boot pad? There it is. 20 seconds. Now, that means that removing this one step almost doubled the rate of our reaction. The reaction took almost half as much time to take place just by removing that one step. That's the power of a catalyst. That's what a catalyst will do for you. Now, what if you want to slow the reaction down? What if that's too fast for you? What if you want to slow it down? Well, one way we could slow it down is by adding extra steps to the mechanism. Now, the step we're going to add to this mechanism is going to be brought to us by a chemical called an inhibitor. And the inhibitor will slow the reaction down by adding steps to the reaction. I'm going to make the inhibitor the first step. What do you think this is going to do? Boop. All right, now we're going to do the same thing, right? Except this time, I'm going to put myself in a little bit of pain for the sake of science. Okay, are we reset?
Yeah.
Okay. In 5, 4, 3, 2, 1, go. Time? 1 minute 54 seconds. So 60 plus 50 is 90. 1 minute 54, 94 seconds. So take a look at that. Putting this stupid little thing in there, our base rate was 36 seconds. This more than doubled the amount of time this reaction took to happen. So that's what an inhibitor does. An inhibitor makes a reaction go slower by adding an extra step. Let's calculate the rate and see what that comes out to. For the first one, 2,000 divided by 36 gives us a rate of 55.52 sig figs, 56 milliliters per second. So every second we can expect 56 milliliters to pass through into the other beaker. 2,000 divided by 20. For the catalyst, that was a flat 100 milliliters per second. And I can't believe I needed a calculator to figure that out. 2,000 divided by 20. 100. Okay, let's try the next one. 2,000, we'll divide that by 94. That comes out to the 2 sig figs, 21 milliliters per second. So, check it out. As the amount of time it takes increases, 20, 36, 94, the rate decreases, 100, 56, 21. Don't confuse time and rate. They're not the same thing. They're the opposite of each other. The more time it takes, the slower the rate. And the less time it takes, the faster the rate. And that's how mechanism and reaction rate work, and how adding a catalyst to an inhibitor can change your reaction rate from the base rate of your reaction. That's it.
Okay, so I hope that video was valuable. I hope that video helped your understanding. I really like Mark Rosengarten. He's a clever guy, and I've always liked his content. So big shout out to Mark Rosengarten. You do great work. All right, so if we go back to our slides here, got another message from Al Lowe. It's an emoji. I'm not sure what it means, but hey, thank you for being here. By the way, also there was a gentleman in here who was spamming the chat, asking for a shout out repeatedly. I think it was about 9 or 10 times. You know, sometimes I think about assigning a mod or getting a moderator for my live streams. It doesn't seem necessary because most people in these streams are so cool. But that jackass that just spammed my chat kind of makes me wish I had a moderator. So if anybody's interested in being a mod, feel free to reach out to me, and we can talk about making you a moderator so that you can catch douchebags like that in the chat and remove them. So I can do, you know, the actual streaming. I would appreciate it. All right, so in that video, we saw that the smallest funnel is what determined the speed with which that water could be poured, right? The water can only be poured fast enough that it will only be poured as fast as the smallest funnel in that chain of funnels will allow. And similarly, the rate limiting step of a reaction, the reaction can only proceed as fast as the rate limiting step of the reaction will allow. So in this example, right, the example that we've been talking about throughout this presentation with the NO2 and the Cl2 becoming ClNO2, the first step of the reaction, this one up here, is slow, significantly slower than the second step of the reaction. And so the first step of the reaction, in this case, is the rate limiting step. It determines the rate, or it limits the rate of the chemical reaction. So we can look at it graphically right here, and Victoria, I think this is where your question will be answered. So this is basically a diagram of the progress of the reaction from reactants all the way to products, the progress of the entire mechanism, right? So the reactants are up here. This is energy on the y-axis and the reaction progress on the x-axis. So you start out with your reactants, right? And for the first step of the chemical reaction, as in any step of a mechanism, it requires energy, right? It requires an activation barrier to overcome that barrier and become the product of that first step, right? And so this little valley here, this minimum right here, or local minimum, I should say, this represents sort of the intermediates, right? But that's not necessarily the highest energy part or the most unstable part of the graph, right? It's these guys up here. These are the most unstable parts. These are called the transition states. So the transition states basically like, you know, the molecules of the reactants are kind of broken apart. You know, those bonds have kind of broken, and the bonds in the products have kind of formed, sort of like halfway in between. It's like the transition between the reactants and products, right? Or at least the reactants of one elementary step and the products of that elementary step, the transition state. So that's the energy maximum, or the local maximum of energy, right? Transition state, the most unstable species in the mechanism. So once step one is finished, you have this local minimum here that represents the intermediates, right? And then the second step of the reaction, step two, also has an activation barrier, although notice that the activation barrier, right, the difference between this guy here and this guy up here, that activation barrier is lower than that of the first step, right? So this all goes back to the Arrhenius equation, where we understood mathematically that a higher activation barrier, according to the Arrhenius equation, results in a slower reaction rate. And so it makes sense in the context of this graph, right? Because a moment ago in the previous slide, we understood that the first step of this mechanism was the slow one, the rate limiting step, right? The one that determines the rate of the overall reaction. And so it's slower because it has the higher activation barrier. So you have step one, activation energy, you overcome that. You have step two, you have the activation energy, you overcome that, and then eventually you form the products. And notice that this particular chemical reaction is overall exothermic, meaning that the energy of the products is less than the energy of the reactants. So overall, this process releases energy. It's energetically downhill, so to speak. So if we look at this, so I got a couple of messages in the chat. Victoria says, yeah, that definitely answers my question. It helps to see the graph with each activation energy. Awesome. I'm so glad I could help. Thank you for your feedback. And I would also hope that if I wasn't helpful, or if whatever I'm doing sucks, that you would let me know about that as well. Don't worry about hurting my feelings. I can take criticism just fine. Got a message from Kai. It says, you're doing an amazing job, Ben. Oh, thanks so much, man. I really, really, really appreciate it. So, okay. So we talked about this. We're continuing our discussion on this two-step mechanism, right? And we just saw a moment ago the sort of humps, the camel humps, as I call them, the activation barriers, and how the activation barrier for the slower step is higher than the activation barrier for the faster step, right? And so each one of these elementary steps, step 1 and 2, they have their own characteristic rate constant. And they have their own characteristic rate constant because, again, each of them have their own characteristic activation energies. The activation energy, the first step happens to be larger than that of the second step. So we expect K1 right? This rate constant for the first step to be smaller than the rate constant for this reaction here, this step here, K2. So if we wanted to write a rate law for this chemical reaction, right? So the rate law of a chemical reaction is simply going to be the rate law of the rate limiting step. Let me repeat that because it's not written on the slide, so I just want to make sure we all understand that. The rate law of the overall reaction is going to be the rate law for the rate limiting step, for the slowest step, right? Because it is that slowest step that determines the overall rate for the chemical reaction. So the rate for the reaction is going to be the rate of your rate limiting step. In this case, it happens to be the first step. That's the slowest step. So if we wanted to write the rate law of this reaction predicted by this mechanism, it would look like this. Rate equals K times the concentration of NO2 times the concentration of Cl2. Why is that? Well, because a moment ago we were talking about molecularity, right? This step represents a bimolecular process where we have one NO2 molecule slamming into one Cl2 molecule, right? And when you have a bimolecular process of two different chemical species, the rate will be the rate constant times the concentration of one of those species times the concentration of the other species. By the way, if anybody doesn't understand any of this, I would sincerely hope that you would let me know in the chat, or even better, you can call in. You can use Discord to call into the show. If you do call into the show and it's not working, or if I don't see you or something like that, just let me know and we can figure it out. I'm relying on you to help me figure this out because I'm still very, very new to all this stuff. Okay, so again, summary of this slide here is that the rate law of the chemical reaction is the rate law of the rate limiting step of the chemical of the chemical reaction, right? And so far in this discussion, we've been talking about how reaction mechanisms are never proven, right? They are only validated, okay? Because again, you can't interview the molecules to figure out where they've been, right? And so keeping that in mind, there are two conditions that must be met in order for a reaction mechanism to be considered valid. If either of these two or both of these two conditions are not met, then the mechanism is invalid. So what are those two conditions? Well, the first condition is something that we kind of went over previously, which is the sum of the elementary steps must be equal to the overall chemical reaction, right? The equations for the individual steps of the reaction, when you add them together, they must equate to the overall balanced chemical equation for the reaction. And the other condition that must be met in order for a reaction mechanism to be considered valid is that the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. So that's kind of a big blurb of words, so allow me to explain. So again, the way that kinetics works, or the way that kinetics is used to elucidate or validate reaction mechanisms, is it's done experimentally, right? And experimentally, you can measure the concentrations of reactants, you can measure the concentration of products, but you cannot measure the concentrations of intermediates. And remember, the intermediates are those things that get produced in one step and then consumed in another, right? So when you're performing a kinetic experiment, since you can't measure the concentrations of intermediates because as soon as they're produced, they're consumed right away, experimentally, the only type of rate law that you can determine, right, the only type of rate law that you can write out, rate equals K times whatever, has to be in terms of concentrations of reactants and or products. It cannot be expressed in terms of concentrations of intermediates. And so this last little blurb down here says that there are no intermediates allowed in the rate law. So again, the rate law being predicted by the mechanism being consistent with the experimentally observed rate law, basically that just means that you can't have intermediates in the rate law. And so we're going to see how this works when we do a couple of examples. By the way, if you find this stream valuable, I would thoroughly appreciate if you slap a like on it, and if you're feeling super generous, consider sending a super chat if you find this valuable. All right. So going back to the reaction that we have been discussing, this whole time, right? So we can see here, we went over this a moment ago in a previous slide, but I think it's worth revisiting at this point. So one of these two conditions we can see is clearly satisfied. So this mechanism, this two-step mechanism, satisfies the condition that the sum of the individual steps must be equal to the overall chemical equation, right? So that condition is met. We don't have to worry about that. Now the second condition, right, which is that the the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. In other words, no intermediates in the rate law. Well, that condition is also met. Why? Well, because we can see that the rate law that we got by the mechanism, right? And again, the way that we arrived at this rate law up here, rate equals K times concentration of NO2 times concentration of Cl2, the way that we arrived at that rate law is by understanding that the first step of the reaction is the slow one, the rate limiting step. And so the rate law of the overall reaction is simply the rate law of the rate limiting step. And so this is how we arrive at this equation up here. And it is consistent with an experimentally observed rate law. Why? Because there are no intermediates, right? NO2, if we look down at the overall chemical equation, NO2, that's a reactant, that's not an intermediate. Cl2, also a reactant, that's not an intermediate. So our rate law does not contain any intermediates, which means that it is consistent with any experimentally observed rate law, which means that it satisfies the second condition. Finally, which means that this mechanism here is indeed a valid mechanism for this chemical reaction. So I got another message by Victoria. It says, would catalysts also not appear in the rate law? Kind of jumping ahead a little bit. I haven't talked about catalysis yet, but catalysts are similar, right? There's something that gets produced in one step and consumed in another, or at least they get consumed in one step and then regenerated in another. That's a better way to put it. Yeah, catalysts get consumed in one step and then regenerated in another. So basically what catalysts do, I'm going over this very briefly, but catalysts basically provide an alternative mechanism that has lower energy transition states, lower activation energies to speed up the reaction overall, because remember, as the activation energy increases, the rate of reaction decreases. So by providing an alternate pathway with lower energy transition states, lower activation energies, you're speeding up the chemical reaction. So got another message here from Crazy Wolf. I really like that name. It says, so the slow step is called the rate determining step. How do you tell which one is the rate determining step if you don't know how fast? Well, typically, to answer your question, let's say if you're being tested on this, you'll be given that information. The only other way to figure it out would be to perform a kinetic experiment yourself in a laboratory. And there's lots of different ways to do that, depending on the nature of the reaction and the equipment that you have and what can be measured. But yeah, typically that information, if you're talking about like a test or a quiz or something like that, that information will be given to you. It'll tell you which one's slow and which one's fast, and you'll have to use that information to arrive at a rate law. So, okay, so far. The mechanism that we looked at, right? We were able to arrive at a rate law. Okay, we were able to arrive at a rate law for a mechanism with a slow initial step, with a slow first step, and that was fairly easy, right? Because we had the rate is equal to concentration of one reactant times concentration of another reactant. Because the first step was our rate limiting step, we didn't have to worry about any intermediates appearing in our rate law equation, right? Now, what if we had a mechanism in which the first step was fast, right? And the rate limiting step appeared somewhere else within the mechanism, either the second or third or fourth or whatever step. So if the first step is fast and the rate limiting step is some other step, how would we determine the rate law predicted by the mechanism for that type of mechanism? So I'm going to walk through this problem here. So it basically says, consider the following reaction. We have 2H2 plus 2NO yields 2H2O plus N2. And it says that the experimentally determined rate law is rate equals K times concentration of H2 times concentration of NO2 squared. And it says to show that the following proposed mechanism is consistent with the experimentally determined rate law. Now, I really like problems like these. I really do. And the reason why I like problems like these is because you can't bullshit your way out of it. you can't cheat to the answer, because this is like you have to show your work, type of problem. So let's unpack what's going on with this mechanism. So if we look at this first step, now we got these funky looking arrows right here. Does anybody in the chat happen to know what these funky looking arrows mean? What do these funky looking arrows here, these backwards and forwards arrows, what do they show? Anybody? I sometimes I wonder how fast or how much time is in the delay between when I say something and when you guys hear it and when it appears in the chat. Because I don't know if nobody's answering, or if just because I haven't given you enough time to answer yet. I still haven't quite figured that out. Okay, so we have a couple messages in the chat that I'm seeing now. Crazy Wolf says equilibrium. Victoria says equilibrium. You guys are both correct. If I had a gold star or a piece of candy to give you, I would. So yes, this represents an equilibrium. So basically what's happening here, right, is that the first step is fast. The second step is slow. Now, because the first step is fast and the second step is slow, the product of the first step sort of builds up, and it doesn't react very quickly because the second step is so slow. And so you have the product of that first step building up and building up and building up and building up to the point where the substances on the right-hand side of this equation, the products, actually react with one another. In this case, this decomposes to form the reactants. So you have both a forward reaction taking place and a reverse reaction taking place simultaneously. It's called a dynamic equilibrium. Both of these processes, the forward reaction where you have two nitric oxide molecules reacting to form N2O2, that process is happening at the same time the N2O2 is breaking down into two nitric oxides, right? Dynamic process. And what these two arrows mean is that they're in equilibrium. And what equilibrium means is that the rates of the forward and reverse reactions are the same. In other words, this process, the forward process where the NO is becoming N2O2, that is occurring at the same speed, the same rate as the opposite, N2O2 becoming NO. And we're denoting the rate constants of these two processes. The forward rate constant we're calling K1, and the rate constant associated with the reverse reaction we're calling K minus 1. So hopefully I've explained the context well enough. If anything is unclear, I would certainly appreciate you letting me know, and we will go ahead and move forward. Okay, so the first step is, like I said, N2 becoming N2O2, but again, the products build up to the point where they're in equilibrium, right? Forward and reverse reactions happening at the same time. The rates of those reactions are the same. In the second step, you have H2 reacting with N2O2 to produce H2O plus N2O. That's the slow step. That's the rate limiting step. So that's the step that determines the overall rate of the chemical reaction. And then finally, in the third step, we have N2O plus H2 yields N2 plus H2O. And it looks like my N2 is missing a state of matter. Shame on me. I should have put a little G there. I know it's really not important for the purpose of understanding mechanisms, but I don't know. I'm a perfectionist, which is why I believe I was attracted to chemistry in the first place. Okay, so again, the goal here is to show our work. We want to show that this proposed mechanism is consistent with the experimentally determined rate law. So how do we do that? Well, remember that, and if you just give me a moment here, I'm going to copy this information and paste it to the whiteboard so that I can scribble some equations and algebra down. So where is it? I think I found it. Nope, there it is. Okay. So I'm going to select all. No, not that. Select all, copy. And we are going to go to the whiteboard. Here we are. And oh, I know what I did. Sorry guys, thank you for bearing with me. Okay, so we're at the whiteboard. I'm going to take this whole thing because it's tiny and resize it. Does that look good for you guys? Can you guys read that? I know that's a little small, but I kind of want to make it small because there's going to be a lot of information that I'm going to be writing in as we follow along with this problem. So any feedback y'all can give, I would certainly appreciate it. So, okay. So the first step, right, is to... The first thing that we want to do in tackling a problem like this is to see whether or not the first condition, right? Remember, there are two conditions that must be satisfied in order for a mechanism to be considered valid. The first one is that the steps of the reaction must equate to the overall equation, right? All the steps, all the sum of all of these elementary steps must be equal to the overall reaction, right? And so if we start looking at what we can add to, if we add these three equations together and look at what we can cancel out, well, it looks like there's an N2O here and an N2O here. What else? Are there any other intermediates that we can cancel out? So Crazy Wolf asks, would N2O be the intermediate? Yes, it is. It is an intermediate. But we also have another intermediate. Can you find it? Yeah. It's the N2O2, right? It's produced in the first step and it's consumed in the second step, right? There's no N2O2 in the overall reaction equation. So it looks like to me, okay, so for the reactants of the overall equation, we have two H2s. There's an H2 there and an H2 there. We have two NOs, right? So we have two NOs right there. And then on the product side, we have two H2Os. So there's one H2O there, one H2O there. And then we have N2. And again, shame on me for not putting the G for gas right there. Okay, so we have just successfully determined that the first condition is satisfied. The sum of the individual steps do indeed equate to the overall reaction equation. So the next step, right, is that the rate law predicted by the mechanism must be consistent with the experimentally observed rate law. Now, in this case, we know what the experimentally the experimentally observed rate law is, right? Sorry, I'm a newbie at this. I'm trying to highlight something, and this is proving more difficult than I imagined. Okay. So this is the experimentally observed rate law, right? Rate equals K times the concentration of H2 times the concentration of NO2 squared. So we have to show that the rate law predicted by the mechanism is consistent with the experimentally observed rate law. And so how do we do that? How do we do that? Well, recall that the rate law for a chemical reaction is simply the rate law for the rate limiting step of the chemical reaction. And the rate limiting step, of course, is this one right here, the slow one, right? And so the rate is going to be equal to K, in this case K2, right, times the concentration of H2 times the concentration of N2O2. Right? Got a message from Peace and Love, says, hey, how are you doing? Or, hi, how are you doing? I'm doing very well. How are you? And thank you very much for dropping into my stream. I wholeheartedly appreciate it. Okay, so the rate of the reaction is the rate law of the reaction is the rate law of the rate limiting step, right? And so the rate law of the limiting step looks like this, where we have rate equals K2 times concentration of A2 or H2 times concentration of N2O2. And I hope we're all following along. If not, please let me know, and I can back up and re-explain something. I don't always do a great job of explaining. In fact, I very rarely do a great job of explaining. So Okay, so this must be the rate law of our reaction. However, this rate law isn't going to work because there's no way that this rate law predicted by the mechanism can be consistent with the experimentally observed rate law. And the reason why is because N2O2, right, this guy over here, is an intermediate. And the rate law for an overall reaction can never have an intermediate in it, right? The reactants are H2 and NO. They're not N2O2, right? So this is a problem, right? Our rate law has an intermediate, but our rate law can't have an intermediate. How do we solve this problem? And the answer to how we solve this problem is that we can express the concentration of the intermediate in terms of the concentrations of other species, reactants or products, usually reactants, right? And the way that we can do that is by understanding a few things about chemical equilibrium. Now, I haven't talked thoroughly about chemical equilibrium yet. I think we might do that in the next live stream series. If anybody has any feedback on what you'd like to discuss in the next live stream playlist, let me know. I don't have any plans for it. So by understanding a couple of things about equilibrium, we're going to be able to express the concentration of this intermediate N2O2 in terms of the reactants, right? And so if we look at this first step, right, earlier we said that this is a dynamic equilibrium. Both the forward and the reverse reactions are happening at the same time and at the same rate. That's what equilibrium means. So the rate of, and I'll just say the rate of the forward reaction, rate sub F, is equal to the rate of the reverse reaction, which I'll call rate sub R. And again, this is all step one, right? So the equilibrium process that is characterized by step one, this equation, rate forward reaction equals rate reverse reaction, this equation applies to step one, the fast equilibrium step, right? So if we set those rates equal to one another, well, and if we express those rates in terms of rate law, well, the rate of the forward reaction is going to be K1 times the concentration of NO squared. Why is it NO squared and not just NO? It's because of this too. We have two NO molecules. This is a bimolecular process, two of those molecules colliding together, right? So that's the rate of the forward reaction, and that must be equal to the rate of the reverse reaction, which was going to be the concentration of N2O2 I messed that up. Let me try that again. I forgot the K. It's going to be K minus 1 times the concentration of N2O2. And that doesn't have anything squared or anything because that's a unimolecular process with just one molecule in it. Got a message that says acid-base titration calculations for the next one. Okay. Yeah, I would love to do that, but I think understanding acids and bases really relies on understanding equilibrium. Like, I don't think you can understand acid-base really well unless you have a solid foundation in your understanding of equilibrium. So I might have to start from scratch on that because I don't want to jump ahead to something that I haven't really talked about yet. But anyway, but I do appreciate the question. Don't get me wrong, I really do. So, all right. So, sorry, I'm going to backtrack just a little bit here. So the rate of the forward reaction is equal to the rate of the reverse reaction. So these are the expressions for the rate laws of those reactions. And so if we solve for N2O2, right, if we solve for concentration of N2O2, well, in this equation, we can simply divide both sides of it by K minus 1, right? And so what we end up with is N2O2, or the concentration of N2O2, equals K1 over K minus 1 times the concentration of NO squared. Okay? So again, the reason why we're doing all this is because the rate law predicted by the mechanism has to be consistent with the experimentally observed rate law. And in order to be consistent with the experimentally observed rate law, it cannot contain any intermediates. The rate law of our rate limiting step has an intermediate in it, and so we need to express that intermediate in terms of reactants. And the way that we do that is by understanding this equilibrium relationship between the rate of the forward and the rate of the reverse reactions. So we just found an expression for the concentration of N2O2, right? So that's this thing right here. So if we take that, I'm going to try to get fancy here. If you guys, if you guys will bear with me, I'm going to try to get fancy here. Okay, so here we go. All right, so I'm going to lasso this N2O2, right? I'm going to lasso that, and I'm going to drag it away, and I'm going to take this expression, which is equivalent to the concentration of N2O2, and I'm going to drag it in and substitute it right there. Look at that. Look at that. I'm slowly learning. Might have taken 7 live streams to figure this out, but hey, better late than never, right? Okay, so we end up at this sort of long-winded equation over here, and I'm going to clean this up a little bit. I'm just going to say that the rate is equal to K1, K2 over K minus 1 times the concentration of H2 times the concentration of NO squared. Yeah, by the way, this is, I just realized this is a typo. This should be NO. This shouldn't be NO2. There's no NO2 anywhere in here. So, yeah, I messed that one up. If anybody caught me on that, yeah, I apologize for the confusion. I really do. So, let me see if I can fix that. It doesn't look like I can, but okay. You guys understand that this is a typo over here. This should say NO. It should not say NO2, right? So just keep that in mind, and I do apologize for the mistake. Okay. So this is the equation that we have right here, where we have, whoops, go back to the pen. So rate equals K1, K2 over K minus 1 times concentration of H2 times concentration of NO squared. Well, this K1, K2 over K minus 1, that's kind of a long-winded way to express a constant. Because if you think about it, a constant times a constant divided by another constant is a constant, right? And so we can simplify this down, and I'll do it in blue here. Actually, I'll do it in green. We can simplify this down to rate is equal to K, we'll just call it K because, again, a constant times a constant divided by a constant is a constant, times the concentration of H2 times the concentration of NO squared. So, again, this problem wasn't really about like finding an answer so much. It was about showing your work. It was about showing your knowledge, that you're familiar with the fact that the rate law of a reaction is the rate law of the rate limiting step of the reaction, and if that rate limiting step has any intermediates in it, which is often the case when the first step of the reaction is fast and the second or third step or subsequent step is slow. If the rate limiting step, if the rate law has intermediates in it, you must find a way to express the concentration of those intermediates in terms of reactants and or products, usually reactants. Okay, so that was one problem, and if it's all right with you guys, I'm going to move on to another one. By the way, thank you guys all for being here. I truly appreciate it. It looks like I'm up to a record 9 likes during my live stream. I'll take it. So if anybody is new to the channel, welcome. I would certainly appreciate your subscription. I looked at my analytics fairly recently and determined that, or I found that about 98% of the time spent watching my content is by people who are not subscribed. Only about 2% of the time spent watching my videos is from subscribers. So that represents an opportunity for me to recruit some people or convince some people that this content is valuable. And the way that I can do that is, of course, by providing value, which I hope I've done tonight. So if you haven't liked the video, I'd appreciate it if you do. And if you're feeling super generous, you can consider sending a super chat. All right, so we're going to delete all this, and we're going to start with a fresh slate here. So I'm going to go back to the PowerPoint here, and it looks like I need to go back into this mode. So that was the problem that we just did, and this is another problem. Okay, so it says consider the following reaction where we have two ozone molecules, two O3s, reacting to form 3 oxygen molecules, 3 O2s. And it says the experimentally determined rate law is rate equals K times the concentration of O3 squared times the concentration of O2 to the minus 1. To the minus 1, that seems a little weird, but I think it'll make sense as we go forward in the in solving this problem. And so, of course, just like the last example, we are tasked with showing that the following proposed mechanism is consistent with the experimentally determined rate law. And so we have the first step here, O3 becoming O2 and O. This is the fast step, and the rate limiting step, the slow step, is an O3 colliding with an O to form 2 O2s. So just as in the last example, the first step is the fast one, the second step is the slow one, and so because the products of the first step are building up and building up and building up, and they can't react fast enough to be consumed, they're being produced faster than they're being consumed, they react with one another in an equilibrium sort of way, which is represented by these forward and reverse arrows right here. Okay, so we're going to solve this one. If you'll give me just a second here, I'm going to copy this over and bring it to the whiteboard. Trying to get fast at this so there's no lag time here. Okay. All right. So just as we did, you know what, I think I could probably enlarge this a little bit. It seems a little small. But of course I want to know what you guys think. Is it too small? Is it too big? Is it just right? Let me know. That sounded weird. Anyway, let's move on. So, wow, I just realized that's the same reaction. I didn't copy I didn't copy the one that I was trying to. Give me a second here. Okay. All right, guys. Thank you for staying with me and bearing with my incompetence. Victoria says, I think that's the one we already did. Yeah, you were right. You were right. It is. It is. Thank you for catching me on that. So I got the correct one up here now. So, all right. So this is a reaction. So I'll try to go through it a little more quickly. I don't think I have to explain it as much because we've already gone through one, but nonetheless, I don't want to leave anything important out, right? So of course, the first thing that we can do is to make sure the first condition is satisfied in that the sum of the steps is equivalent to the overall reaction. So let's see if that's true. It looks like we're going to look for some intermediates we can cancel. Looks like there's an O here and an O here that we can cancel. Okay, so we end up with 2 O3s. Looks like we have our 2 O3s, one in the first step, one in the second. And we have 3 O2s. It looks like we have 2 O2s in the second step and 1 O2 in the first step. So it looks like that first condition is satisfied, right? The sum of the steps is equal to the overall reaction. And when I was copying this, I don't know why it didn't copy over, but I just want to make sure we understand that this is slow and this is fast. Okay, so the rate law of this chemical reaction is going to be the rate law of the slowest step, the rate limiting step of the reaction. In this case, it's the second step. So we get rate is equal to K2, because we're talking about the second step here, K2 times concentration of O3 times concentration of O. But just like we saw in the previous example, we cannot leave that bare. Why? Because this lonely oxygen here, this monoatomic oxygen, is an intermediate. It's produced in the first step and consumed in the second step, and so we cannot leave that in the rate law equation. There's no way that this rate law, as it's written currently, can be consistent with the experimentally observed rate law. So we have to express the concentration of the intermediate and concentration of reactants and or products. So the way that we do that is by using this equilibrium relationship with this equilibrium reaction here. So we understand that the rate of the forward reaction is equal to the rate of the reverse reaction, and so that means that K1 times concentration of O3, right? K1 times concentration of O3, that's the expression for rate of the forward reaction, is equal to K minus 1 times concentration of O2 times concentration of just plain old O, right? So this is the expression for the rate law for the forward reaction. This is the expression for the rate law of the reverse reaction. Since this is an equilibrium, that means these rates are equivalent. Anytime you see these two arrows, that always means that the rates of the forward and reverse reactions are the same. So the intermediate, that's what we want to try to express in terms of concentration of reactants and products. And so this is what we're going to solve for algebraically. So we're solving for O, which means we need to divide both sides of this equation here by this term here, this K minus 1 O2, right? And we get that the concentration of O is equal to, I'll just say K1 over K minus 1 times concentration of O3 times divided by concentration of O2. Now, another way to express this, and it looks like I haven't really drawn this very well, so I'm going to take this up here and kind of lift it up so that it's on the right level here. Okay, so this is our expression for the concentration of O, right? Now, there's a way to sort of clean this up a little bit. So, in other words, in order to take this O2, this is just something that's a preference by a lot of people. It's not necessarily something that you have to do, but this is the way you'll often see it written, is that you generally won't see concentrations in the denominator of a fraction. You'll see it just all on one line. And so if you have something in the denominator and you want to put that all on one line, the way that you do that is by putting it on that one line and raising it to the power of minus 1, right? 1 over something is the same as whatever that thing is raised to the minus 1 power, right? And so this is the same as, let's see if I can scribble some of this out. So that expression that we just saw is equal to concentration of O3 times the concentration of O2 to the minus 1. So, and again, all I did was just pulled that concentration of O2 out of the denominator and expressed it in the numerator by raising it to the power of minus 1. So it's the same thing, just written a little bit differently, right? I hope I didn't lose anyone there, but please, by all means, let me know if I did. Happy to explain it further. Okay, so now we have an expression for the concentration of O. We have an expression for the intermediate, which we can substitute into this rate law equation up here. And so I'm going to shuffle some things around just to make sure I can give myself some room here. I'm going to take you. Whoops. I'm going to take you. I'm going to move you down there for now. I'll take you. And I'll move you. Whoops. I tell you, it's the software. It's not me. Never my fault. All right, and I'll put you back over here. Okay. So thanks for bearing with me. All right. So again, this concentration of O here, right? This is the term that we're trying to express in another way so that the rate law predicted by the mechanism can be consistent with the experimentally observed rate law. And so if we just substitute this in, right? Take that and just kind of through. Come on. Lost my fraction bar. If we throw that down there, then we get this convoluted looking equation right here where we have rate equals K2 times concentration of O3 times concentration of, or excuse me, times K1 over K minus 1 times concentration of O3 times concentration of O2 to the minus 1. So there's definitely a way we can clean this up a little bit and make it look much nicer. And so that'll be rate is equal to, well, just like we saw in the previous example, a constant times a constant divided by a constant is a constant. And so we can simplify K2 times K1 over K minus 1 as simply one constant, which we can call K, times the concentration of O3. And that's going to be squared. Why is it squared? Well, because we have two O3 terms. We have one right here, and we have one right there. And the only thing left in this rate law equation is the concentration of O2 to the minus 1 power. And so take a look at that. It looks like the rate law predicted by this mechanism is indeed consistent with the experimentally observed rate law. Okay, so I think I'm going to leave it there. Getting kind of tired. What are we, about an hour and 15 minutes in? So that is going to do it for the chemical kinetics lesson part of the live stream. So from here on out, in this live stream, I'm just going to chat with you guys if you're interested in sticking around and just kind of shooting the breeze for a little bit. Thank you so much for tuning into this live stream. Once again, if you want to watch any of the other volumes in this chemical kinetics live stream series, you can click on the link for the playlist. It's called Chemical Kinetics Live Streams. It includes all of the volumes of this playlist, of this chemical kinetics series from volume 1 all the way to the end. Right now we're in volume 4, but pretty sure we're going to do another one